Welcome to this lecture series in linear algebra. In this lecture, we'll state and prove the Cayley-Hamilton theorem, but in a form that is not found in textbooks, as far as I know anyway. So basically, we will prove one version of the Cayley-Hamilton theorem. Let us recall some of the things that we need. So fix a endomorphism, and suppose Px is an eigenpolynomial of the endomorphism. Then the geometric multiplicity of the eigenpolynomial is defined as this number. The algebraic multiplicity is defined as this number, or in other words, it is the set of all the, or rather dimension of the space of all the generalized polyeigenvectors corresponding to Px. It turns out to be equal to that. Alright, then we define the saturation exponent of this eigenpolynomial as the smallest positive integer, which when you raise pt to the power 2, you get that the dimension of this thing is same as the algebraic multiplicity. So the algebraic multiplicity is the dimension of this thing, but what saturation exponent captures is that you may not need to go all the way up to dimension. It may suffice to take a smaller power, and the smallest that suffices is the saturation exponent. Alright, and we also saw that the saturation exponent is at the same time the greatest positive integer for which px to the power r, the greatest r for which px to the power r divides the minimal polynomial of t. So it's interesting that the saturation exponent has two descriptions, where one is obtained by taking a minimum of something while the other is obtained by taking maxima of something. Okay, so this is something that we saw. And one more remark is that these containments are all strict. So this is contained in that, but strictly, and so on up until the saturation exponent. And again, this is something that we have seen so many times, but the reason for this strict containment is that once, first of all, suppose there was some containment somewhere that was not strict, meaning it was an equality, then every successive containment will also be an equality. That is something that we have seen way earlier. And if that is the case, then the minimal polynomial will not remain the minimal polynomial, because a smaller exponent here would suffice. Basically, you will be able to create a smaller degree polynomial, non-zero, which will vanish on the endomorphism T. So let me not go into the details of this, but we have seen this earlier. Also recall that the degree of Px divides the dimension of any of these things. For all m, in fact, m greater than or equal to 0 could also have been written. So this is one fact. And lastly, let us also recall that if this is the set of all the eigenpolynomials of T, then the sum of all the algebraic multiplicities for all the eigenpolynomials is same as the dimension of V. This is also something that we have proven earlier. So all of these facts will be used, maybe some of them will be used, and maybe more facts from other things, from this may not be an exhaustive list of all the facts that we need to use, but anyway, this should suffice. So let's start. So we will define what is called what I call the characteristic exponent. I do not think this terminology is standard either. This is in all probability a non-standard terminology. So fix an endomorphism, and suppose Px is an eigenpolynomial of T. Then the characteristic exponent corresponding to this eigenpolynomial, or of this eigenpolynomial if you want to express it that way, is defined as, the notation is this, and the definition is you take the algebraic multiplicity and divide it by the degree of P. So that's the definition, and this is an integer, so note that chi pt is an integer. The reason is very simple. This is divisible by the degree of Px because this is dimension of kernel of pt to the power dim v, and as we recalled, kernel of pt to the power any integer, any non-negative integer, is divisible by degree of Px. So algebraic multiplicity is always divisible by the degree of the corresponding eigenpolynomial, and hence this is an integer. All right. Here is an interesting lemma that the characteristic exponent exceeds, may not strictly exceed, but it is at least the saturation exponent. Okay, so this is what we have stated. Fix an endomorphism, fix an eigenpolynomial of it, then the characteristic exponent is at least the saturation exponent. And yeah, so this is also fairly straightforward given all the facts that we have in our hand. So say, for simplicity of notation, that S is the saturation exponent. And as we recalled in the beginning that all these containments are strict. Okay. At the same time, each of these dimensions, the dimension of this, the dimension of that, so on, the dimension of this, are all divisible by the degree of P. So this is at least a degree of P, and therefore this is at least 2 times the degree of P, right? This is divisible by degree P, this is divisible by degree P, but the strict containment means that this has to be at least now twice of degree of P, and so on and so on. If you continue that reasoning, the dimension of this should be at least S times the degree of P, and therefore, okay, so the dimension of the kernel of P to the power psi Pt, which is same as S is same as that by notation. So this is at least psi Pt times degree of Px. But what is this dimension? By definition of the saturation exponent, this is the algebraic multiplicity. And now if you just divide both sides by degree Px, we obtain the correct inequality. So very nice, we have that. And now we can state and prove the Cayley-Hamilton theorem. So fix an endomorphism. Let this be the set of all the eigenpolynomials of T, and define this polynomial capital Qx as the product of all such things. So you take Px and then raise it to the characteristic exponent. Okay. So this is defined, and this is called the characteristic polynomial of T. The point is, this is 0. Qt is 0. And this is straightforward now. I mean, the Cayley-Hamilton theorem stated in this way is not much of a trouble once we have all the pieces. So why is that? Basically, we will show that the minimal polynomial divides this guy. But what is the minimal polynomial? So let mx be the minimal polynomial. Then by definition, or no, I mean not really by definition, but by what we recalled. Yeah, so first of all the irreducible monic factors of mx are precisely the eigenpolynomials. And by what we recalled about the saturation exponent, this is nothing but px to the power saturation exponent. Okay, and now since this exceeds the saturation exponent for all p, we have this product divides that, but this is by definition the characteristic polynomial, and this is the minimal polynomial, and that's it. So once the minimal polynomial divides something, that something will vanish once you evaluate the endomorphism in place of x. So yeah, so this proves the Cayley-Hamilton theorem. And now you can object as to why are we calling this the Cayley-Hamilton theorem? Because the Cayley-Hamilton theorem that one reads in textbooks is about determinants. Determinant of a certain matrix, the roots of it are precisely the eigenvalues, and the determinant vanishes once you plug in the endomorphism in place of the variable, etc. But we haven't discussed determinants. We will do that later, and which is when we will connect this version of the Cayley-Hamilton theorem with the determinant version of it, and that will take some time. But this is how I like to think about or present the material. This is how it is organized in my head. So this is how I do it. Yeah. Now let us draw one corollary out of all this work, which is interesting. What is the degree of the characteristic polynomial? So again, we have the same setting. We have some endomorphism. We have set of all eigenpolynomials. Okay, and then the minimal polynomial is, or rather the characteristic polynomial is product all eigenpolynomials raised to the power characteristic exponent. Alright, but what is the degree of Qx then? The degree of Qx is sum the degree of each factor, which is some degree Px times the characteristic exponent, which is by definition of the characteristic exponent same as the algebraic multiplicity. But as we recalled, this is same as the dimension of the vector space. So the degree of this guy is the dimension of V. And we have already seen that the minimal polynomial divides this guy. Therefore, the degree of the minimal polynomial is also at most the dimension of the parent space. And that is what we have recorded here. And this is an interesting conclusion because the way we showed the existence of the minimal polynomial only gave us the bound of the square of the dimension of V. Because what we did was we had T, then we considered all these vectors in this space, and then we showed that a linear combination of them must vanish. But since the dimension of end V is the square of the dimension of V, this gives just a bound of the square of the dimension of V on the degree of the minimal polynomial. But this reasoning shows that since there is a polynomial of degree at most dimension of V, in fact exactly dimension of V, which vanishes when you replace x by the endomorphism, the minimal polynomial cannot have degree more than this. And hence, the degree of the minimal polynomial is at most the dimension of the parent space. A non-trivial conclusion by all this work. Alright, so this is where I would like to end the lecture. As usual, like, comment, share, subscribe, and I will see you next time.